So we're going to start topic 4 here, oscillations in this lesson. So this will be our kind of introductory version before we get into it more deeply. And the first thing we need to basically say is that we have our one fundamental equation that's going to govern what we do for oscillations. There are more complicated versions, and it's something called Hooke's law. And we're going to come back to it after I kind of write it down here just to show you where we're starting. It's Hooke's law, and it basically is this. The force of a system is equal to negative k, which is just some constant. We'll define that later, times x, where x is the displacement from equilibrium. So now we have to kind of define some of these points. Looking at this tells us that acceleration is proportional to negative of the displacement, which means if you were to graph it, it would look something like this, negative slope kind of thing. And I'll put two dots here at the end where this is acceleration, this is displacement from a point. We're going to call that point equilibrium, and we'll define it in a second. But it'll look something like this, and we'll have these little points where we get as far away as we possibly can, because you can imagine if the acceleration is in the opposite direction of your displacement, that means if you're over here to the right, the acceleration is going to try and pull you to the left, and if you're over here to the left, the acceleration is going to try and pull you to the right. So it'll look something like that. So let's go ahead and start by defining this equilibrium. Basically, in a system, this is the point where net force is equal to 0, which should make sense. We've talked about equilibrium before, but in this kind of situation, it's going to be where this is displacement from equilibrium. So here it would be when x is 0. It's how far you are from there. Here you'd be 0 from it, so it'd be this little middle point. The classic example that follows Hooke's law is a mass on a spring. So let's say we have a spring attached to a wall, right, and then a mass attached to it, and it's on some frictionless surface here, right, and this mass is here. In this case, the spring constant would be k. It's basically how strong this spring is, because you can imagine that a slinky versus the coil on the suspension of a car are both springs essentially, but one is much stiffer than the other. So the bigger k is, the stiffer the spring is. So the slinky would have a really low k, and the coil on the spring would have the coil on the suspension of a car would have a very high k. But it would be this. And if we just leave this sitting here, nothing happening to it, then this point right there is the equilibrium point. It's the point right there where it's not, the spring isn't stretched or compressed at all. Then x would be either to the right or to the left, the distance from equilibrium, as like say we grabbed this block and we stretched it out over to here, kind of a thing, right? We stretched the mass out over to here. Then however far we stretched it out, or however far it was from this equilibrium position, that would be what x was. And it can change as this thing would maybe move. You could imagine if we pulled this out and let it go, it would just bounce back and forth. And so x would be something that was a function of time. It would change its position, but it's that position relative to the equilibrium. And you can count it as positive in either direction. All we care about is how far from equilibrium it is, but there are some instances you care about whether or not it's stretched or compressed, and whether or not it's to the left or the right. Sorry for my coughing. I'll try my best not to, but I'm still trying to get over a cough. Next thing is amplitude. That's supposed to be an A, an amplitude. And this is your maximum displacement, so your maximum x. So however far over, say, the maximum that this stretches over, if this is x max, then it equals amplitude A. Okay? Amplitude, that's a capital A. And that's our variable for it when we use it as this capital A. Okay? It's a capital A. Equilibrium has no symbol for it, really. It's just x is equal to 0. So you don't have to worry about anything like that. But this is maximum displacement from equilibrium. Next little thing we need to define is a cycle. This is essentially the time it takes for something going in this kind of cyclical motion, this repetitive motion back and forth, is the amount of time it takes for it to do one full cycle, to go there and come back. Say we started it here, let it go, it would come bounce over here and then bounce back. That would be one cycle. If we looked at it from the middle, it would be how far it went away from the middle. Now, it comes back to the middle and you think, oh, it's back where it started, that's one cycle, except it's back where it started but going in the opposite direction, so we have to let it go all the way over here and then come back to equilibrium again, and now it's at the same place going in the same direction. That would be one cycle. So you have to be careful. It's not just getting back to the same place, it's getting back to the same place and going in the same direction. Okay, so that's a cycle. Next thing is frequency. Frequency. This is essentially this essentially tells you how quickly it's going through cycles. It's essentially the number of cycles per time. Cycles doesn't really have a unit, so this essentially has a unit of a 1 over a time, and in SI units that's a 1 over a second, which we define as a new unit called hertz, which is just an HZ. Hertz is a 1 over a second, so it's cycles per time. That's supposed to be an E. Cycles per time. Something very closely related is period. Period we use is essentially the reciprocal of this. So period, which we use a capital T as our unit for that, basically stands for time, but it's a capital T because it's a special time, because it's the time to complete one cycle. So that makes it essentially time per cycle, which is the reciprocal. It's equal to 1 over the frequency, which is time per cycle. So like I could ask you, what's the period of Earth's orbit? And you would say it's 365 days or 1 year. What's the period of Earth's rotation? You would say it's 24 hours or 1 day, because Earth rotating around once is one cycle, and so therefore it takes 24 hours. It's 24 hours per one cycle, or 1 day per cycle, or 1 year per orbital cycle. Just depends on the cycle and everything like that. And its units, of course, then are just in time. They're in seconds. Okay? But it's a capital T because it's a special time. It's not just any old arbitrary time. It's the time for a cycle. Okay? But it is a time. Next thing is phase or phase difference. I'll put it in parentheses. But phase is essentially where in the cycle, like, so if we have a wave like this, the phase is kind of like where in the cycle you are. And if I had another wave that, say, maybe was like going like this or something like that, you would say these two waves are out of phase, because if I drop a line at any point, they're at different parts of their cycle. Here, this one's at a max, and this one's like near a minimum. Of if we had two different waves like next to each other, they would be out of phase, and then the amount that they would be out of phase, if they have the same frequency and everything like that, the amount that they would be out of phase would be the phase difference, and it's usually measured in radians, because that will make more sense later when we get into how we actually do the math for this, but it'll hopefully make more sense later. Now we're doing stuff that's angular, and I think I'm going to go ahead and just throw this chart out here for you. This is something you're going to want to kind of keep tucked in your back pocket all the time, because we're not doing it necessarily in this video, but we are going to get into doing stuff where you have to do stuff with rotational, circular type motions. You know what? Never mind. I think I'm gonna hang off on that. I'm not gonna put that chart down till we actually get to circular motion. So never mind. This video is gonna be too long. So let's just forget about that for a moment. Let's just go ahead and move on to what is called simple harmonic motion. Okay, or abbreviated SHM. Simple harmonic motion. Essentially, simple harmonic motion is any motion that follows or obeys Hooke's law, which, if you remember from above, was F, which is called a restoring force, and it's called a restoring force because it equals negative constant times the displacement. So it means if I displace to the right, this force tries to pull it back to the left. If I pull it to the left, this force tries to push it back to the right. That's what this negative sign means. It's negative of it, so that makes this a restoring force. It tries to push it back to where it came from. We have some constant and we have a displacement. So if a force is proportional to the negative of the displacement, then the motion that will result from just that force alone will be simple harmonic motion. The best example of this, again, is the mass on a spring. If we have a mass attached to a spring, it fits Hooke's law, right? K is the spring constant. K doesn't have to necessarily be the spring constant. We'll have other examples in a minute where it's not. The mass is there, and it'll be simple harmonic motion. If I pull this and stretch it out to the right, it'll bounce back and forth. Assuming this is frictionless, it'll bounce back and forth between the two amplitudes. The maximum displacement, I'll pull it off to the right and let it go. So I pull it off to the right 5 centimeters, let it go. It'll go to negative 5 centimeters, then the positive 5 centimeters, then the negative 5 centimeters, then the positive 5, and it'll just keep going back and forth if there's no friction. If I pull it out to 10 centimeters, it'll go 10 to negative 10 to 10 to negative 10, and it'll bounce back and forth between them. Okay, as long as you don't overstretch the spring such that you bend the metal and warp it and ruin the spring. Okay, so it basically describes the motion of this thing, and so I'm going to do something here that I believe just the higher level needs to know, but you don't need to know how to derive it. You're going to have to kind of memorize it, but the derivation is not really too horrible. If we look at it, and it comes all just from this equation, so I want to show it to you once, and then maybe later when you actually have to do the derivation out, you'll get it, and as you get more into calculus, you'll get this with your math careers here. So we have F equals negative kx, so I'm going to write it down again. Equals negative kx, and so this is just m times a equals negative kx, because that's what f is, ma, which means I can solve this to a equals negative k over m times x. And if you remember, acceleration was basically what's called a time derivative. It's the slope of the velocity versus time graph, and velocity is the slope of the displacement versus time graph. So it's like the slope of the slope. And so when you get into calculus, we do instantaneous slopes, and they are called derivatives. So essentially, if we take position and take one time derivative of it, one time slope of it, we get velocity. If we take another time derivative or another time slope of it, we will get velocity. So I can write this as d2x, and don't worry if you don't understand what this means yet, because you're not required to know this here just yet, but you'll basically get this. A second derivative of position is equal to the original variable times the negative of some constant, just times some constant. And it turns out one of the solutions to this that solves this thing, basically a function x as a function of time, that if we were to take two derivatives of it, and when you come back and watch this later after you've learned what derivatives are, this will click for you immediately. If we take two derivatives of it, we end up with exactly what we have there, is something of the form of this. Some number a, I chose a for a reason, if you remember up above what I said a was, so a times the cosine of omega t, which if you know your trigonometry, this omega is the angular frequency, and then the time, plus b, some other number, times sine of omega t. All right? And this, if you take two derivatives of it, will give you something of this form. Okay? And so if we start doing these derivatives, we can get something pretty quick. So the first derivative of this would be velocity. So velocity as a function of time. The derivative cosine is negative sine. So this is negative a, and then derivative cosine and then you have to do what's called the chain rule. You'll learn that later. Is negative a omega sine omega t plus derivative sine is cosine b omega sine omega t. And again, when you get into doing derivatives, you'll be able to do this yourself. And you can come back and watch this video. Now, one more time derivative will give us acceleration, right? Which is what we want, acceleration. And this is equal to derivative sine is cosine, so negative a, and then we have to take this omega out of the inside, so a omega squared cosine omega t minus, because derivative sine is negative cosine, minus b omega squared, oops, I wrote sine there. Hold on, that should have been cosine that I wrote there. My mistake. So this was b omega cosine. Derivative cosine is negative sine, so it goes back to being sine, and then our omega t. We brought that one omega out because you have to do the derivative of what's on the inside, which is just omega, and you get omega squared. And so we have this. And if you look at this, if I bring this omega out in front, just real quick, it's negative omega squared times a cosine omega t plus b sine omega t, which if you look at this little part in the parentheses is our original equation here. So we have negative omega squared here is this. So a as a function of time is equal to some constant times x. This is what x is. So this would be a equals negative of some constant times x, because this is x. This here, this part here, is x of t. So this actually does fit this equation here. There's another version that fits this involving exponentials. It's a little simpler, but you don't really know exponentials that well yet, so I'm not going to do that. But you know sines and cosines, and you can see that right here. And if you remember the graph of sines and cosines, they go back and forth, right? Up and down, just like this would go back and forth, back and forth. And you can imagine if I took and hooked a pencil or something onto this, a pin, right? I hooked a pin onto this, and then as I set this going back and forth, right? I let this oscillate back and forth in simple harmonic motion, and then I took a piece of paper, kind of like a seismograph, you know, kind of thing, and I pulled the piece of paper underneath it nice and steadily. What would it do? It would draw out that wave motion across the paper, and it would be a sine or cosine graph. And if you graph this, that's what you'll get. You'll get this picture here through time as it moved back and forth through time. Now we can take this a little step further. This here is our general solution right here for position. This is our general solution for velocity, and this is our general solution for acceleration. But we don't know what these A's and B's are. Well, they depend on what are called the initial conditions. So we can actually reduce this down a little bit by looking at a specific situation. So let's say our specific situation is that we grab this mass, we pull it off to the side, and we let go of it. So at time t equals 0, we're going to start it right when we let go of it. When t is 0, our displacement is equal to a. It's a maximum. So if we look at this equation here, right, we need x of 0, right? We need this. Sorry, let me write the whole equation. X of t equals a cosine omega t plus b sine omega t. Okay, so let's write that down again. So at t equals 0, this has to equal just the amplitude, just the x max. So x max has to equal x of 0, because that's where we pulled it off the side and we let it go. It's never going to get further away from that. It can never get more energy than that because we're not going to touch it again. So what happens here is we plug in t equals 0. So this is a cosine of 0, omega times 0, plus b sine of 0. And this has to equal x max. Well, what's the sine of 0? Well, the sine of 0 is 0. So it doesn't tell us anything about this. What's the cosine of 0? cosine of 0 is 1. So this tells us that A here is equal to x max. In other words, we just figured out that this A, and I told you I picked that letter for a reason, is the amplitude. Okay? But we don't know what B is. We know that A isn't 0, we know A is the amplitude, but we don't know what B is. So let's try looking at the velocity. So velocity as a function of time was negative A omega sine of omega t plus B omega cosine of omega t, right? And now we want to look at what's the velocity at the very start. So I grab this thing, I pull it off to the right, and I let go of it. How fast is it going right when I let go of it? Well, I've just let go of it, so it's not moving at all yet. The spring hasn't had a chance to accelerate it and give it velocity. So at v of 0, this has to equal 0, right? So whatever this is has to equal 0. Just like this had to equal the amplitude. Well, here, let's try it. This is negative A omega sine of 0, because t is now 0, plus B omega cosine omega t. Oh, I'm sorry. Cosine of 0. Right? Well, sine of 0 is 0. So this goes to 0, right? And then therefore this whole part's gone. This whole thing is 0 because sine of 0 is 0. But look over here. Cosine of 0, this is 1, which means B times omega has to equal 0. Now we have two choices here. Either B is 0 or omega is 0. If omega is 0, this is trivial. It means we have nothing happening because this is our angular frequency. It defines how quickly it's moving back and forth. If this is 0, it means it's not moving back and forth and we have no problem. Nothing is happening, it's just sitting there. So that's trivial. We're not interested in that. So if we're not interested in this being 0, because that means nothing is happening, it means we're only interested in B equals 0. So therefore, B equals 0 with this initial condition where we pulled this off to the left and let it go. That means if B is 0, we can come back to these original three equations and we can reduce them. So given the initial conditions, we can reduce the above to x of t equals a cosine of omega t. V of t is equal to negative a omega sine of omega t. The velocity is in the opposite direction of the position, which should make sense, at least at the start. Depends on what we talked about before. It depends on the phase. And then the acceleration is equal to negative a omega squared cosine of omega t. Okay? And so given those initial conditions, we can reduce it to this. Now you have to be careful because I can also, there are initial conditions that all depend on where you look at the start. So imagine instead of me starting with it displaced, let's say I walked up and it was right when I first started looking at it, it was at equilibrium and it was already moving. So it was at equilibrium and it was headed to the left. In that case, I would go through and do something very similar, except x of 0 wouldn't be equal to the amplitude, it would be equal to 0, in which case a would have been 0, and so a would have been 0, and the cosine would go away, and then v of 0 wouldn't have been 0, it would have been the maximum speed, in which case b would have ended up being the amplitude, and the sines and cosines here would have switched. This would be more like b, or we could switch it to a, because now b would be the amplitude. It'd be a sine omega t, and a omega cosine, and a omega squared sine. They would flip-flop them. And there are even more complicated situations where I could walk up and start timing where it wasn't at the amplitude and it wasn't at the equilibrium, but it was somewhere over here off to the side, in which case it would stay looking like this. And the actual amplitude would be some combination of, dependent on A and B, they'd both stay, and cosines and sines would both stay. And if you want to try it on your calculator, try graphing cosine of theta plus sine of theta. And you'll find it still looks like a sine wave. It still gives us one of these waves. It'll just be shifted either left or right some. But basically, this version here is usually what you're going to do. It's the simplest to do. The second simplest is if you start it at equilibrium, but it's already moving, in which case the cosines become sines and the sines become cosines, and everything else there stays the same. You just have to be careful about how the situation starts, about whether or not these are sines or cosines. At this level, you're unlikely to do anything that involves having cosines and sines in there together, like in these three versions. So these are the ones you really need to know. You really need to know best. And then just switching out sines and cosines as we get to that kind of stuff. So how does this graph out? Now, this is, again, this part here I think is something only the HL needs to know, but it also is good to see this work because, one, it shows us that we can turn this simple harmonic motion, this here, into something that looks like a wave, into a sine graph. So it looks like a wave if we pull the paper through it. So as time goes through, it draws out a wave, kind of like a seismograph would. And two, so it's good for helping understand that that's where, you know, our wave stuff is going to be based on this simple harmonic motion, that waves are a version of simple harmonic motion. And two, it helps us to graph these out. So you need to be able to identify and do these kind of graphs. So let's do position versus time graph. Well, here's time, here's position. Well, position is a cosine. Cosine starts at 1 and goes down. Oh, it's not very great, but draw a cosine line like this, something like that. Oops, I don't know why that happened. And then when you look on here, you'll have